of yet another new family of high-temperature superconductors, also called iron-based superconductors, or iron pnictides and iron selenides. This story is almost 10 years old, so you see that the progress develops quite continuously. And as a conclusion, you see that it took almost 70 years to get first accelerator, so maybe now it's a time that some application of existing system will come to industry and technology, or some new system will be discovered soon, so the progress can really be anticipated. So what do we know about experimental evidence of superconductivity? As I said, certain materials like tin or mercury demonstrate the drop of resistivity at certain temperatures, while some other materials like copper don't show that effect. This is associated with the formation of Cooper pairs, as we discussed on one of the first lectures of superconductivity. The Meissner effect is related to the fact that magnetic field doesn't penetrate into the superconductor, contrast to normal metal, while this has to be discussed in more close details, because in reality there are two types of superconductors. So as you may see, that magnetic field actually destroys superconducting state through the pair breaking effect. So to say, as we discussed Landau criterion, one can say that there is a current associated with applied magnetic field which exceeds the critical value necessary for pair breaking, and as a result, at sufficiently high magnetic field, the superconducting state is destroyed. So on the phase diagram, magnetic field versus temperature, you may see that there is a domain of existence of superconducting state, and superconducting state disappears also at sufficiently high temperatures and sufficiently high magnetic field. And this system which demonstrates such phenomena are called type 1 superconductors. However, there are other systems where, as the phase diagram is a little bit different. So what you see on this diagram, that in fact the same property, that at sufficiently high temperature and sufficiently high magnetic field, the superconducting state disappears. However, there are two critical magnetic fields, so to say. And what happens at first critical, BC1, then the state without any vortices, so to say, any topological defect, similar to the phase of type 1 superconductors, appears. However, if the magnetic field exceeds the first critical field BC1, but still below the second critical field BC2, then what happens that the vortices start to form, and the vortices which are topological defects, which consist of the normal phase, so the superconductor phase is destroyed along the core of the vortices, however, remains between vortices. So this is a way of creating of the lattice of the vortices. The very same way the lattice of the vortices is formed in the rotated superfluid. So in this sense, magnetic field and rotations play the very same role. So you increase magnetic field further, you create more and more vortices. We discussed that circulation is quantized. So this is a system, this is entirely quantum system, and then if you reach the upper critical field BC2, then the superconductivity is completely destroyed. So you see that the mechanism of destruction of superconductivity is different, and it's also important technologically, because this system which can keep vortices inside, this type of superconductors is called superconductors of type 2. It's also important for technological purposes, because having superconductors which can resist high magnetic field and still be a superconductor is important, in particular for construction of superconducting magnets. That's all what I wanted to tell you about type 1 and type 2 superconductors. Now let's be back to pairing mechanism. And I really like this cartoon. Then what happens that electron propagating through the crystal actually interacts with the lattice vibrations, which are the phonons. And what appears is that the pair which propagates along the crystal and talking to lattice vibration have all chances to be paired. So the lattice vibration provides a pairing mechanism, and also quite intuitively, if we increase temperature, we increase the lattice vibration, and it leads to destruction of the pair. This is how phonons influence and mediate the superconductivity, provide a mechanism, and as I already mentioned, the theory of Barling-Cooper-Schrieffer was developed in 1957. The paper was published in 1957, and they got a Nobel Prize in 1993. So to say it again, so phonons create attractive potential for two electrons, and as a result, the Cooper pairs were formed. We discussed that the typical size of the Cooper pair is associated with a gap. So the gap in spectrum of elementary excitations of superconductors is gapped, and this gap actually controls the size of the Cooper pairs. And according to the gap taken from the experiments on specific heat or in tunnel current experiment, tunnel junction between normal metal and superconductor, this gap is of the order of few kelvins, which means that the size of Cooper pair, which is inversely proportional to the gap, is quite big. Therefore, to speak about the bound state of just two electrons as a formation of Cooper pair is not an appropriate language, and it's much better to say that the ground state of the Fermi-liquid ground state of the metal is unstable at sufficiently low temperatures with respect to formation of the Cooper pairs. So the symmetry, namely U1 symmetry, is broken, and therefore the phase transition to the superconducting state occurs. And in the most of the system in the world, in most of known superconductors, the mechanism of pairing of electrons to form Cooper pairs is mediated by phonons. And as we have discussed, in most of the superconductors, the Cooper pair is the singlet. In order to break the Cooper pair, one needs to pump energy of the order of 2 delta, which then destroys this paired state. Let me briefly flash also ideas of the BCS theory. In particular, the same kind of superfluid state is now observed in ultra-cold gases in optical lattices, where, as you may see, since the coupling constant is first of all attributed to the Fermi momentum and the scattering length, it has nothing to do with phonons. The mechanism is purely electronic. However, the same type of BCS state can be observed, and what one can see from the superfluid, fermionic superfluid state in the optical lattices, that first of all, that the temperature of superfluid or superconducting transition is 0.3 of the Fermi energy. So it's no more Debye frequency, which stands in front of the exponent. And then the exponent, this is exponent to the minus pi over 2 kf and modulus of the scattering length. You may also see if the scattering length goes to infinity, this is so-called unitary limit. And those who attend lectures of Professor Bloch and Professor Zoller have heard about unitary limit. So unitary limit of Fermi gas being fine-tuned by Feshbach resonance actually provide this exponent being equal to 1, and therefore the temperature of superconducting transition can be as high as 0.3 of the Fermi energy. Would the same be possible through electronic mechanism in the metals, you can imagine that the Fermi energy, typical Fermi energy, is from 1 to 10 electron volt, which means from 10,000 to 100,000 Kelvin. So there will be superconductivity with a temperature of about 1,000 Kelvin in such system. Okay, and the superconductivity, as I said, is related to pairing mechanism mediated for BCS, original BCS model by phonons. For more general models, may be mediated by anything else. For example, magnons, excitons, and so on and so forth. However, if we specify certain attractive potential, we can write down the Hamiltonian, what we did by deriving BCS, and diagonalize it by different means. I showed you how to diagonalize this Hamiltonian by minimizing the total energy with respect to U and B coefficients, which are connected through the determinant, so which defines as a sphere on which we rotate. However, there are many other ways one can do molecular field approximation, or one can do variational approach. And original Bardian-Cooper-Schrieffer paper, if you read it, and I recommend to go to library, take a journal, original derivation of Bardian-Cooper and Schrieffer was a little bit different. They used the variational wave function in order to construct the wave function of the ground state. So this is the way they did it, but as a result, after you apply in the field or you do variational procedure, you arrive at certain quadratic Hamiltonian, which can then be diagonalized, and diagonalization of this Hamiltonian establish connection between this molecular field parameter delta, which plays the role of the gap in the spectrum, and which leads to certain equation, self-consistent equation, which then actually explain several phenomena. First of all, it explains existence of the gap in the elementary spectrum of the excitation. It also explains, assuming the temperature dependence given by this equation, that the phase transition is the second order phase transition, and produce all critical exponents conforming this statement. This is the variational function of Bardian-Cooper-Schrieffer theory, and you see that instead of varying, well, one can write it that way, and these are famous UV coefficients, Bogoliubov coefficients, which I used in the derivation given on one of the lectures in order to minimize the energy. Okay, let's now come to discussion of high temperature superconductivity. So, in contrast to simple systems like mercury or like tin or like binary alloys, niobium, germanium, or magnesium diborite, where the crystal lightness is sometimes very simple. It contains one or two atoms in elementary cell. The first real high temperature superconductor, which is yttrium, barium, copper oxide, with a critical temperature of 92 Kelvin. After you dope this system with additional oxygen, the crystalline structure is like that. It's about 20 atoms in elementary cell, so the system is really complicated as itself. So therefore, one needs to subtract simple ingredients necessary for the theory, and this is what I'm going to discuss step by step now. So the message which is written here says that it's now experimental evidence that the parent mechanism is not the phonon mechanism. So I'll in addition to the fact that this system is real high temperature superconductors, it also tells us that the mechanism of such superconductivity is different from the mechanism explaining superconductivity in a simple compound. Therefore, as I said, the challenge is first of all to understand this mechanism, and I should say that although it's already 30 years since discovery of superconductivity, there is still no consensus about mechanism. There is no unique mechanism which explains everything. Therefore, it's still challenging. Maybe you are young. Some of you may contribute to understanding of this phenomenon. And since there is no understanding, not yet understanding of the mechanism, there is no real understanding of which system one needs to look for. Of course, in the discovery of the superconductors, it was clear that the superconductivity should be found in the family of this Cooper oxide. So people start to use other Cooper oxide compounds like lanthanum Cooper oxide, mercury-based Cooper oxide. But most of these things were done by just empirically. But by checking parent compound, they checking similar compound in the hope that there might be higher temperature of superconductivity, and sometimes it happened. However, there is no strategy, and this is kind of another challenge, that there should be strategy in the search and in the hunt for new high temperature superconductors. This is what I said. The record, I'm not sure, this was recorded for like 5 years ago. I'm not sure that it is a big change, might be some increase of temperature by 10 Kelvin. And you see that the compound which demonstrates this temperature is based on mercury, thallium, barium, calcium, Cooper oxide. And this is non-stoichiometric system. You see that while it's non-stoichiometric from the point of view of oxygen, it's non-stoichiometric from the point of view of hydrogen, and it's non-stoichiometric from the point of view of thallium. So you see how many parameters one needs to change in order to achieve the highest possible temperature superconductivity. And at the same time, this high temperature superconductivity also possesses the highest HC2. This is what on the previous slide was called BC2. This is upper critical magnetic field, which is above 1 million Gauss. Okay, this is how the history developed. This is mercury 1911, then lead, niobium, niobium nitride, niobium carbide, niobium 3 tin, niobium 3 germanium. And it took, as I said, 70-something years when the temperature was increased from 4 Kelvin up to 24 Kelvin. And then it was a breakthrough with lanthanum, barium, Cooper oxide. This is the system which Bednorz and Müller got a Nobel Prize for, and then it's almost vertical step with a new compound. However, there was a breakthrough around 1986, 1990, and then again the system saturates. There is no that big progress as one could anticipate during last decade, while meantime new systems which have nothing to do with Cooper oxides were discovered. One of this very prominent system, promising system, is this iron-based superconductors. Okay, now we are about to discuss key ingredients of necessary for construction of successful theory of high temperature superconductivity. So we need to discuss what is common for these high temperature superconductors based on Cooper oxide family. So first of all, copper and oxygen form planes. So you see that both, it's probably not that good to see it here. I show it in the next slides. That The systems which I just showed you as examples are related to extra doping of by the oxygen. So at stoichiometric state, these systems are insulators, as many ceramics are. Ceramics is you have your cap, your mug for tea or coffee, and this is ceramics. However, if you dope this ceramic, which is very, very good insulator, and bring additional carriers to the system, it suddenly become bad metal, but at the same time good superconductor. And as I said, taking the picture from neutron scattering and, for example, and reconstructing the crystalline structure, lead to conclusion that both oxygen and copper form planes. So the first hint was that the superconductivity is quasi two-dimensional because the main action happens in the copper oxide planes. Yeah, it also supports the measurement of the Fermi surface done with angle resolved photo emission, also supporting this argument that the Fermi surface is two-dimensional, kind of cylinders. So this is a typical Fermi surface, and this is a cartoon coming from reconstruction. As you see, the copper sits in the corners of square, and oxygen sits in the middle. So each oxygen is divalent, so it contains, so it forms the p orbitals, which they'll contain coppers. And the Fermi surface, as I said, forms arcs. This is two-dimensional Fermi surface, and this is very close to so-called square. And square is those who solve the problem which I suggested, namely to build a Fermi surface for tight binding models, in particular in two dimension. If you take a tight binding model with, on a square lattice with neighbor hoppings at half filling, you will get that your Fermi surface should occupy half square of your brilliant zone, and it's a square. I think you discussed it also with Professor Mercier. If you take into account the hopping beyond the next neighbors, you will find the curvature of arcs. Then the Fermi surface deviates at half filling from the perfect square, and perfect square also means that it is so-called nesting. What is nesting? Your Fermi surface have pieces of measure 1, not measure 0. So square is measure 2, line is measure 1, point is measure 0. So the Fermi surface, which is the surface, which is anyway measure 1, has congruent pieces, and congruent means if you take the reciprocal vector, you can translate this part of the Fermi surface to this part of the Fermi surface. If you calculate certain response function with such a Fermi surface, for example, you want to calculate Linhart function the very same way as we did it for the spherical Fermi surface, you will find that the polarization operator, which is density-density correlation function, or spin susceptibility, which is spin-spin correlation function, is logarithmically divergent, where logarithm contains the upper cutoff, which is a Fermi energy, and low cutoff, which is a deviation from the half filling, or temperature, or anything else. So you will get divergent logarithm, which then immediately assumes existence of strong correlations. In addition, you have Van Hoff singularity for the same type binding model in the corners, which gives you yet another logarithm. So some of the correlation functions are divergent as log square, and some of them are divergent as log, which was already hint that one needs to find this direction, which will then be connected to this divergent correlation function and produce a pairing mechanism. So to say, what can we learn from this slide is the shape of Fermi surface, the quasi two-dimensional structure of the lattice, and necessity to find a mechanism which will then couple this together. This is yet another system of bismuth strontium oxide. See how complicated this system is. So, and having said about this mechanism, people immediately start to think about Coulomb interaction. In particular, so-called Hubbard interaction, since the system at stoichiometric condition is localized, as I said, it's insulator. Moreover, it was discovered that this insulator is antiferromagnet, which was yet another indication that it has something to do with the Hubbard model, as we discussed on our previous lecture on Monday. So people start to consider Hubbard model. However, in perfect Hubbard model at half filling, as I said, it is antiferromagnetic insulator. One needs to add certain holes which superconduct. As I said, the superconductivity appears because you dope system with oxygen, which produce extra holes, but the sign of Kerr is not so important. One of the first attempts to explain superconductivity was to consider the two-dimensional Hubbard model slightly away from half filling. But then it was very quickly understood that since the background is antiferromagnetic and you introduce holes inside of antiferromagnet which will then proliferate along your antiferromagnetic background, the symmetry of the superconducting order parameter should not be spherical. What we discussed on the blackboard and what was discussed in the theory of Barlin-Cooper-Schrieffer was spherically symmetric gap, which even didn't depend on the momentum, not to say angle, which was sufficient to explain superconducting properties of simple conventional superconductors. However, in the high temperature superconductors, it was found that the symmetry of superconducting order parameter is not S-wave. So the order parameter is not isotropic, is not spherically isotropic, and after very long debate, I remember I was like 20 years younger, it was very hot debate about experiments and theory, whether it's still S-type superconductor or something else. And then one of the precise experiment with Josephson junction provide convincing evidence that the symmetry of the parameter is D-wave, and therefore it led to yet another argument against BCS theory of superconductor, which always leads to the S-wave superconductivity, because phonons cannot provide such anisotropy in general. Of course, one can think about sophisticated theories, but in simple theories, it's very difficult to understand that phonons can cause such high asymmetry, and besides existence of nodes in the superconducting order parameter. So the conclusion was that high temperature superconductors are D-wave superconductors. So D-wave, so S is orbital moment L equal to 0, P is orbital model L equal to 1, and D is orbital model equal to 2. D-wave superconductors are still consistent with singlet structure. So it tells us nothing against that the Cooper pair is singlet. However, D-wave, like you construct a wave function in your box. So the ground state wave function doesn't have nodes by definition, because this is a ground state. The first excited wave function has a node in the center of the well. This is a P state. The second excited state has two nodes inside the well, and this is D state. So this wave function, actually, since we have a two-dimensional geometry, has 4 nodal points on your Fermi surface. Therefore, there are 4 points on the Fermi surface where there is no gap. The gap is closed. So this was what experiment demonstrated. However, as I said, it has nothing against, it says nothing against singlet pair, while for some other strongly correlated systems like strontium rutenite, where the experiment has demonstrated that superconducting is of p-wave. So p-wave assumes that L equal to 1. So there is one node. One node means that the coordinate function, wave function, should be antisymmetric. D-wave coordinate function is symmetric. So in p-wave, a superconductor, the coordinate part of the wave function is antisymmetric, which means that the spin part should be symmetric in order to provide general symmetry property for the wave function consisting of several fermions, and therefore p-wave superconductors are triplet superconductors, where the Cooper pair has a triplet structure. So you should always keep in mind this connection, how many nodes your wave function has, and what kind of spin structure your superconductor can therefore have. So this is again the chemistry. You see that this is a copper 4 orbitals, well, 2 orbitals in 2p orbitals sitting in the corner of the square, and there are 4 oxygens which overlap with the copper orbitals, and you start with a localized Fourier function, and this is the way you construct first the Hubbard model. However, the Hubbard model, which you will then construct, will be based on not single band Hubbard model. As I said, first of all, what happens, the Hubbard interaction splits copper on the 2 subbands. This is what you did. This is Hubbard interaction. And then there is oxygen broadband. There are some gaps here, which for stoichiometric situation is completely filled. So this is how your ground state looks like. So you have empty copper subband, you have gap here, and you have oxygen completely filled. This is why it is insulator. When you dope oxygen, you create holes here, and these holes start to form pairs and superconduct. So therefore, even simplest Hubbard model contains 3 bands: 2 copper Hubbard subband and broad oxygen band. And it was, as I said, clear that this is not phonon interaction, and therefore people start to look for the mechanism how 2 electrons can be paired on the antiferromagnetic background. So to say, one of the ideas was to look for mechanism based either with a spin fluctuation or some resonances in spin system, which then can mediate the superconductivity of these systems. And then Anderson came with a pioneering idea of the resonant valence bonds. So what he said, that this is a cartoon saying how single particle and 2 particles propagate in antiferromagnetic background. What basically Anderson said, that one can borrow some ideas again from the chemistry, and if we remember how benzol rings look like, it contains this hexagon, and in the corners there are carbon atoms. See, carbon has a valency equal to 4, and hydrogen has a valency equal to 1. So you see each carbon is connected to 1 hydrogen and 2 neighbors, but the question is where the remaining valency goes. So it says that this valency can be used to yet another carbon partner. So this is this double line, and therefore it explains the structure of benzol ring. However, the state is twofold degenerate, because one can have a situation when this 2 carbon is paired by 2 valencies, or these 2 carbons hexagon has this symmetry. And therefore, in chemistry it was called as a resonance valence bonds. Anderson used the same terminology and the same ideas in order to borrow it and utilize in high temperature superconductivity. What then happens, according to Anderson theory, is that in your antiferromagnetic state, when you dope it, some spin liquid is formed. So this is not magnetic state at all. So you dope this system until you destroy the superconductivity. So this is the phase diagram. This is hole-based superconductors, typical representative. This is yttrium barium copper oxide and lanthan copper oxide, or a system with mercury, with thallium. So what you see, this is a doping versus temperature. Zero doping means half field material. So at half field you have insulator and antiferromagnet. So you dope system and you destroy the antiferromagnet. Then you dope it further and superconductivity start to develop, and superconductivity forms so-called superconducting dome. So the dome means that there is doping at which superconductivity reaches its maximum Tc. Moreover, in this cartoon it's not that clear, but in principle this dome is not very symmetric. It's not semicircle. So the area below critical doping, which is called underdoped superconductors, is much bigger than the area at dopings higher than critical doping, which are called overdoped superconductor. But there is optimal doping. So what Anderson says in simple word: when you destroy the antiferromagnetic state by doping antiferromagnetic by hole, what is created is a kind of spin liquid. And spin liquid means that you don't have long range order like an antiferromagnet, but you have a short range correlations. And then these short range magnetic correlations can resonate. And this resonated, it's called RVB, resonating valence bond, provide a perfect mechanism perfect non-BCS mechanism, by the way, for high temperature superconductivity. So to say, each elementary electron in your system becomes composite particle. It consists of fermionic particle, let me first finish this sentence. So imagine that each electron is a composite particle. It is fermion. It consists of fermion, neutral fermion, which is responsible for spin degrees of freedom. It's called spinon. And it also contains the charge boson, which is responsible for charge degrees of freedom. Therefore, the pairing is provided by spinons, which form spin liquid, but charges, bosons, form charged Bose gas, which is almost ideal with the temperature, critical temperature, as the temperature of Bose condensation in charged Bose gas. This was Anderson's idea. It has nothing to do with BCS, and in principle, it can provide very high temperatures of superconducting transition, because temperature will be just proportional to the density of carrier. It also explains why the superconductivity occurs at some finite concentration. Well, I should also mention that there are families of copper oxide superconductors where the carriers are electrons. These are mostly cerium-based copper oxides, but you see that this phase diagram is a kind of caricature on the right side. Namely, the antiferromagnetic phase is much bigger compared to antiferromagnetic phase in the hole-doped copper oxide, but the superconducting dome is smaller, and there is also room for coexistence between superconductivity and antiferromagnetic states. A CO means competing order. Here, just to make story even more complicated, there is a room for spin glass state, which people observe. There is so-called pseudo-gap regime, where the gap in the electron spectrum, if seen by RPS, is already visible, but phase coherence is not reached. so the system is not a superconductor. So this is more or less what people understand nowadays about theory of high temperature superconductivity. Again, summarizing the system, this high temperature superconductivity, which are based on copper oxide, are quasi two-dimensional materials. These are electron systems with initially quasi-localized orbitals. Therefore, some strongly correlated models like Hubbard model are highly likely to be responsible for the superconducting property. So two-dimensional strongly correlation. The symmetry of order parameter is not spherically symmetric. It's D-wave. And moreover, the superconductivity develops as a matter of competition between different strongly correlated phases, such as antiferromagnetic phase, superconducting phase. So it looks like that the high temperature of superconductivity is driven by this competition. This is a compromise which system finds. Okay. That's all for the superconductivity. Any questions?
I have a few questions. Is exists any useful natural theory for the high temperature of the parameter?
Well, of course, people can write down this is done. Even more, these competing phases can also be included. So you can write down Ginzburg-Landau theory, which contains more complicated order parameter. By the way, some years ago, like 10 years ago, there was a revolutionary idea that the order parameter, which contains two components, superconducting component, because superconducting order parameter is a complex number, it's wave function, so it contains modulus and phase, or two components, real and imaginary part, and magnetic component, which is three component. This is magnetization vector. So 2 plus 3 is equal to 5. People discuss so-called SO5 theories of superconductivity, which means that your order parameter lives on a five-dimensional world. Moreover, by rotating this order parameter, one can continuously transfer it from fully superconducting to fully magnetic. Such theory with the 5-component order parameters were developed quite successfully, but it looks like that sort of predictions from this theory contradict to experiment. So the theory is really beautiful and elegant, but it looks like that it has nothing to do with that type of high temperature superconductors. Moreover, I would say that studying of superconductivity boosts many elegant theories and actually create a new understanding in several related areas. So it was not useless at all. So people, in their attempt to solve complicated problem, achieved understanding of several other related, closely related problems, and this is how scientific progress develops. Other questions? Okay, let's go to heavy fermions. Heavy fermions actually is much older system. So this table shows what are the systems we are talking about. And you see that some of the systems are metals, some of the systems are superconductors. There are two families of the system, two main families. There are cerium-based systems like cerium copper 6, cerium copper 2 silicon 2, cerium cobalt indium 5, and there are uranium-based systems. It's uranium beryllium 13, uranium rubidium 2 silicon 2, uranium lead 2 aluminum 3. And what is specific about these systems? So some of them are superconductors. And you see that the temperature of superconductivity is of course incredibly low. So it's on the order of few Kelvin or even less than Kelvin. However, as I said, the effective mass of quasi-particles measured through specific heat measurement leads to very high effective mass. of the order of 1,000. Therefore, if the density of carrier is fixed, so Fermi momentum is proportional to the density to the power 2/3, to the power 1/3, sorry, and if we write down the Fermi energy divided by p square on the effective mass, which is a few thousand of mass of electron, we will get that the Fermi energy is also a small number of the order of few Kelvin. Contrast to Fermi energy of conventional metal, which is of the order of few 1,000 or 10,000 Kelvin. Therefore, if one compares the Fermi energy and critical temperature of superconductivity, one can see that there is something like factor of 10 between critical temperature and Fermi energy, which allows to say that these compounds are true high temperature superconductor, not in the sense that absolute high temperature, which above nitrogen temperature. No, measured in units of Fermi energy, this is really very high temperature of superconducting transition. So the puzzle is where these heavy masses come from, and maybe understanding of the mechanism of formation of heavy masses would help us also to understand the mechanism of high temperature superconductivity. So this is what I said, and this slide I already showed you when we discussed the fermions. Typical measure of specific heat and typical plot is a specific heat as a function of a t square. So therefore, the cut of specific heat the measurement of specific heat divided by temperature as t square. So A then gives you coefficient of electronic contribution, which is proportional to the mass of the carriers, and B, coefficient B, which is the slope of this curve, gives you information about phonon contribution. And the Sommerfeld constant, as you see, for three-dimensional metal, for example, is proportional to the mass of the carriers, and mass of the carriers subtracted from the specific heat measurement, and the Fermi energy is given in this table. So you see that for alkali metals, actually the effective mass is very close to the mass of electron, and the Fermi energy and Fermi temperature is of the order of 10,000 Kelvin. This is what I said before. Another way to measure the effective mass is to do so-called de Gas-Van Alphen experiment. We discussed behavior of electron in a small magnetic field and diamagnetic response associated with the quantization. However, one can also proceed with the discussion of behavior of magnetization in the high magnetic field. So then one can see some oscillations with a period inversely proportional to magnetic field. And actually, this experiment of analyzing this oscillation provides you information about the effective mass, which is associated with the maximum cross-section of your Fermi surface. This is yet another way to test the Fermi energy. So what can you see from this table is that the Fermi energy, first of all, is few hundred Kelvin. The effective mass for this system, the highest is in cerium kappa 6 is 500, but there are even systems with even higher effective mass. But these are also few hundreds of the mass. And to make a long story short, as I said, there are two families. One is cerium-based, another one is uranium-based. And the difference between these two families is in position of localized level, which is singly occupied. For cerium-based is 4f orbital. For uranium-based is 5f orbital. The position of this f level related to the position of the Fermi level. In cerium-based system, this localized level is far below the Fermi level. Therefore, there is no hybridization between these electrons and itinerant electrons, while for uranium-based system, this F level, which comes from measurements and calculation, is very close to the Fermi surface. So there are very strong there is very strong hybridization. One can also say that in this system you have spin 1/2 which interact with conduction electrons. So in this sense, the system is with an integer valency regime. And here, since 5F level is very close to Fermi surface, there are very strong charge fluctuation, and this is probably in the intermediate valency regime, because this F level can also contribute to the valency of your compound, of your system. So this is how Fermi surfaces look like. In particular, this is uranium platinum 3 system, if I remember well. And the question is, what are the models, how one can get this high effective mass? This is yet another problem we did not yet find solution, and scientific community is not yet agreed about this solution. However, let me start with some theories which are developed to explain the mechanism of formation of heavy masses in cerium-based compound. As I said, that the model consists of conduction electrons, which are SPD electrons of the conduction band, and localized spins. So, and since the localized spin can interact with the spin density of conduction electron, it produces this storm, which then leads to Conda. I will come to discussion what it is. And there is Heisenberg type interaction between localized model. So this model, by the way, is called Conda lattice. So now we come to discussion one of important effects, which is Conda effect. And what is Conda effect? Let's start with the Hamiltonian given by the first term. So there is a kinetic energy of conduction electron. Suppose that your lattice of spins is very much diluted, and you can investigate, you can forget about interaction between spins and just consider independent interaction of conduction electron, which each spin impurity is separate. And what was discovered in certain pure metals like gold doped with magnetic ions, this was prototype system for this effect, that the resistivity of such system goes up when you lower down the temperature. So it reaches some minimum, then it goes up if the temperature is increased, if we deviate from this minimum, and if the temperature is decreased. So increase of resistivity when the temperature is low down is absolutely counterintuitive effect, because we used to the fact that either resistivity drops and forms superconducting state, or resistivity saturates and up to some residual value and stays flat. Here the resistivity increases, and Conda proposed the mechanism which explains this increase of the resistance. So this is what I said is typical. For green curve, this is superconductors. There is some critical temperature after which resistivity is dropped to 0. Typical example, mercury. Blue curve is copper, resistivity saturates, but what is seen in these alloys is increase of the temperature. So what Conda did, he constructed very simple perturbative theory coming from high temperatures, and first of all he discovered that the theory is renormalizable, and interaction of local moments with conduction electron produce logarithms. So the resistivity indeed grows logarithmically when the temperature is low down. This effect is of paramount importance for nanostructures. Would I have time, I will talk about it. Would I not have time, we will find some another way to speak about it. And actually, the explanation of the Conda effect given just by computing second order of perturbation theory in 1964 boosted development of many branches of modern condensed matter theory. For example, it appears that the Conda model given by this simple Hamiltonian is exactly solvable by Bethe-Ansatz. So the first Bethe-Ansatz solution was done in 80s. Then it appeared that this model possessed certain conformal invariance, so it also contributed to development of conformal field theory, and so on and so forth. So you see that one of the ingredients is Coulomb effect, which actually leads to increase of the inverse transport time because of increasing the backscattering, so to say. What actually happened physically, that interaction of electrons with localized spin increase very much the backscattering, which leads to increase of the resistivity. There is yet another effect if we take into account the interaction between two spins. As I said, from very beginning, we assume that the lattice is very much diluted. However, the same electrons which mediate, which interact with local spins and contribute to Coulomb effect, can also mediate the interaction between two spins. This interaction is known as the Ruderman-Kittel-Kasui-Yoshida interaction. Sorry, it's written in German because, never mind. To make this story simple, with Anton Parafilo you discussed the Linhart function, which is a polarization operator, polarization loop. If one, this is the Linhart function, you can really recognize it. So this is the same polarization loop which you computed with Anton. Now, if one takes a Fourier transform of this Linhart function, what one finds that the Fourier transform is oscillating function of the product Fermi momentum times the distance. So now this is the same Linhart function after taking Fourier transform as a function of dimensions parameter to PFR. What we see here, that first of all, at the long distances, this is a three-dimensional case. The same oscillations exist in one dimension and in two dimensions. The tail of this function is 1 over r cubed. So it's long-range interaction. The distance, short distance behavior, if you Taylor expand this function, produce 1 over r. And what is more important, that the function is oscillating in changed sign. Let's now assume that r is related to the lattice constant of your magnetic atoms. So for example, r is somewhere here. It means that the interaction between spins is antiferromagnetic. If, however, the lattice constant is in this domain, then the interaction between atoms is ferromagnetic, and so on and so forth. So this RKKY interaction can explain mechanism of ferromagnetic or antiferromagnetic interaction mediated by conduction electrons. So if we put two things together, we will find that actually these are competing mechanisms. The same way as antiferromagnets and superconductivity are competing. And moreover, one can use the same ideas which I just explained you for high temperature superconductivity, namely the resonating phase. So Coulomb effect, as I said, on one hand is a localized effect which leads to increase of backscattering, and at the same time it screens the local moment. This is another phenomenon which is well understood and known, that Coulomb effect produces screening of localized moment. On the other hand, it's related to the possibility to flip spin. So what happens for Coulomb effect, that electron flies, and with antiferromagnetic interaction between electron and spin, it can flip the spin of impurity and flip its own spin, and it doesn't cost any energy. And this is the way the screening of the spin occurs. If, for example, the mechanism of the exchange integral is ferromagnetic, it produces no Coulomb effect because the direction is fixed, and you cannot flip both, because you cannot then obey the spin conservation law. However, if you magnetize your system, if you, for example, apply magnetic field which freezes direction of magnetization of your spin of localized impurity, then you will not be able to flip it anymore. Therefore, magnetic field destroys Coulomb effect. But on the other hand, if you have a molecular field associated with interaction between other spins, it plays the very same role as a magnetic field. So to say, the magnetization, so antiferromagnetic or ferromagnetic exchange, competes destructively with Coulomb effect, and in addition, some kind of spin-liquid correlations should be taken into account. What I said actually is summarized in this phase diagram. You can plot the effective temperatures. The magnetic phase effective temperature, or nail temperature, is given by RKQY. It is just second order perturbation of Fourier transform of the Licton function. For Coulomb effect, it's a bit more complicated. The theory, which I said, this perturbation theory, can be resummed or solved by means of renormalization group equation, which leads to certain scale which resembles very much BCS. So you see that this is non-analytic in the coupling constant J, but this is exponential function. D here is a bandwidth. So exponential function is always below power law for small values of arguments. However, at some values of arguments, exponential function grows faster than any power law. So to say this phase diagram, known as the phase diagram of Doniach, tells that for small doping, if Coulomb temperature is much smaller than RKQY, the ground state of the system is magnetic. However, for large doping, it's a situation of the Coulomb singlet, screen state. In the middle, the spin-liquid correlations develop, and these spin-liquid correlations are responsible for formation of the big effective mass and explain the heavy thermal compound. This is one of the class of the theories which I wanted to show to you in very schematic way. But what you see here, that the very same way as in high temperature superconductors, what happens here is a competition between magnetic correlations and local correlations, competition between antiferromagnetic singlet, which is non-local, and Coulomb singlet, and so on and so forth. And the result of competing interaction leads to some strongly correlated effects. Let me speak a little bit about other classes of strongly correlated systems, which are also important for applications. If you ask me what kind of applications heavy fermions are good for, I would first mention the thermoelectric phenomena, because this big effective mass is very important for the Seebeck effect, for conversion of electricity to temperature, or temperature to electricity, and so on and so forth, which is yet another very interesting and challenging field for application. Now we are coming to organic conductors and organic superconductors. These are typically quasi one-dimensional system. In high PC compounds we discuss quasi two-dimensional system because copper and oxygen form copper oxide planes. Here it's basically organic molecules which are elongated in one particular direction. And again, in the early age of superconductivity, in 1964, Little and Ginzburg independently invented idea that reducing dimension, namely coming to low dimensional systems, actually increases correlations and can lead to increase of temperature of superconducting transition, and also lead to some non-phonon mechanism. For example, both Litt and Ginzburg suggested so-called exciton mechanism of superconductivity. Because, again, going to low and low dimensions increase fluctuations, increase correlations, and as we see, competing interactions can lead to high temperatures of compound. So this is how these quasi-one-dimensional systems look like, and here we arrive at many interesting playgrounds for quasi-one-dimensional systems. I already mentioned Latinger liquids as one example, which behave in a very different way than the Fermi liquid. In particular, the excitations in Fermi liquids are electrons and hole, well-defined excitations, which is proven to be true in 2 and 3 dimensions and high dimensions. However, it is also proven that in one-dimensional systems, fermionic excitations do not represent the good language of quasi-particles, because the quasi-particle lifetime is sufficiently short, and the inverse quasi-particle lifetime is comparable with the energy of quasi-particles. So quasi-particles are badly defined. However, the bosonic quasi-particles are well defined. There are many interesting phenomena like spin-charge separation in this system, which was predicted and seen. However, one can also look at spin structures, and one can combine certain one-dimensional system in the chains or ladders. And Professor Nersesyan, for example, made a pioneering contribution to physics of spin chains and ladders. So this is how spin ladders are formed. And one can actually think about dimensional crossover. So suppose that there are some quasi one-dimensional chain of ladders, and you start to couple it weakly and produce two-dimensional object, or you couple it in both directions and produce three-dimensional object. And this is another way to construct theory basing on exact solution for one-dimensional. So good thing about one-dimensional system, that in several cases exact solution is possible, and therefore constructing exact solution for chains and using hopping from chain to chain as a perturbation, one can actually increase dimensionality and construct perturbative solution of high-dimensional system. And the same, the phase diagram here is the temperature versus pressure, is very much complicated. You see that it contains superconducting phase, it contains spin density wave, antiferromagnetic phase, some competing orders. It also competition between local and itinerant structures. But as I said, one-dimensional systems provide, from theoretical point of view, much more controllability, because one can go far beyond perturbation theory. One can avoid using mean field, which is anyway very questionable for one-dimensional systems, and still demonstrate pronounced effects of strong correlations. Okay, I will probably stop here, because you will have a busy day. You will need to have a break before meeting at 11 o'clock. Are there any questions?
Is there some way some duality can be applied for high temperature superconductors?
Now people start to apply this idea of holography and duality to strongly correlated systems, as well as this is very recent direction. There are some attempts. What you are saying, just to explain it to everybody, there is so-called ADS-CFT duality, which maps strongly correlated physics in a bulk to some kind of weak gravity or weak classical behavior on the surface. And this idea appears to be very powerful in high energy physics, and one of the very rapidly growing direction. In high energy, yes, in condensed metaphysics, somehow there are some obstacles to apply. First of all, unlike high energy physics, where there are some compactified dimensions and there are extra dimensions, and say Young-Mills theory are typically in 11-dimensional world, in condensed metaphysics we live in 3, sometimes 2, sometimes 1-dimensional world. So to say, this duality, which relates strongly correlated system to certain classical model, is not yet allowing to solve some particular strongly correlated model. I mean, I'm not skeptical, I'm not saying against this, but for me, big evidence would be if some three-dimensional Hubbard model will be taken, and this is one of the challenge. The problem is not yet solved, and then solved by kind of two-dimensional weakly interacting model. It's not yet done, but it's not saying that it's impossible. It develops, not maybe that rapidly as in high energy, but there are works in that direction as well. Other questions?
In the periodic table, you showed us of the superconductor materials.
Mm-hmm.
Carbon was in yellow, was not neither superconductor neither normal.
Well, I think no. I think carbon was white. Let me Yeah, I cannot tell you what it means. I need to look at. Yeah, carbon. You're right. Carbon is somehow special. Look, I cannot tell you. Sorry. Good observation. I should check myself. What does? But I know, for example, that graphite. What I know about superconductivity of carbon. If you take graphene-like structure, which is quasi-two-dimensional pieces of carbon-based material, because carbon can form a diamond structure, which is three-dimensional. It can form graphite-type sheets. So if you take this graphite bench cake, big, then it's superconducting if you intercalate it with some metals. So you add some metals like potassium in a little concentration, and then this graphite is superconducting. Graphene, single layer, two layer, is not superconducting at all. Yeah, this is what I know. Maybe this is, so it can be superconducting if you dope it a little bit with some. Other questions? Okay, then thank you very much. We still meet before exam on April 4th, and we meet today at 1:25 and go to Electra. So, thank you, and see you in the afternoon. Uh-huh.